then those all get taken here to complex 3. And this is where we do that cool Q cycle, right? So we can send this over, or we can send that. Okay? Now the Q cycle, right, is where we send, right? If we send 2 electrons this way, we send 2 electrons this way, okay, that ultimately gets transported to cytochrome C, we'll just call it site C, which is associated to the membrane. That's where our electrons travel. We would need 2 of those though. How many protons do we pump with 2 electrons? 4, right? That's why we have the Q cycle. We can go over the, Q cycle if you guys want me to. But 4H plus, okay? And then what happens, we have here complex 4 and cytochrome C, remember 2 of those, bring over. Cytochrome C, and then we'll shuttle the electrons, but they're unique because they have the copper. Now here we have iron sulfurs, and we also have hemes. The top one has hemes, okay? We pass it through here. Ultimately, our final electron acceptor is, just make the stoichiometry right, half a molecule O2, and we pump 2 protons. Y'all can do, that's basically the electron transport chain in a nutshell. You're going from a very low reduction potential for NAD+, now it's reduced, and it will want to pass its electrons through these different electron carriers that have increasing reduction potential. That's the main point. It's going in that flow towards oxygen, and by sending them through these intermediates, we harness that energy to do the pumping for us. If it was just transferred directly to oxygen, all that energy would be lost, given off as heat, and there would not be any concerted flow of protons. Okay. Then ultimately, okay, remember this is the intermembrane space. We have here our C10 associated to our A. And I'm fine with you just draw out your, let's see, one more. There's your bell pepper on the inside. Here's your A. Remember how there's that complex that kind of holds it in place beside it? Okay. Remember, that's on the matrix side. And what all these things are going to do, and I think this is pretty cool, is these are all going to flow through here, basically. So they actually start here, hop there, hop back through here. And that's going to power, the flow of those protons is going to power taking ADP plus PI and making it ATP, just like we talked about. Because they have to flow through there, and it's due through conformational changes, right? Those protons have a pathway to travel between this A and these C10 subunits. And as they change their protonation state of the C10 subunits, what happens? It moves relative to the A. As that moves, of course the gamma is coupled through epsilon and the delta, but functionally what happens is the gamma subunit here, as this rotates, that rotates, and it changes the conformation in here to force that. Does Does that work out? Is that okay? Make sense? We learned a lot, I think, don't you think? Cool. That's good. Or we covered a lot. I don't know if we've learned it. But I don't feel like I've been going any faster than anybody else would. So.
Those other two electrons on
Up here?
Yeah, where those-
Yeah, they'll go back, remember, and they'll go back to Q. So we have Q, and they get recombined with Q, and they make QH2.
and then it goes back through like.
Yeah, then it can continue
It
that
just-
cycle. Yeah, it's kind of weird. It's like, why does it do that? But the whole purpose between the cycle is it's actually a strategy to get twice as many protons pumped for the same amount of electrons by cycling it back then. Because when you bring QH2, it has 2 protons. When you separate off the electrons, okay, 2 get freed up, but by sending 1 electron one way, the 2 protons get pumped out. And then bringing in another electron pulls off 2 more protons with it. It's a smart strategy for doubling the amount of protons that you get pumped. And you see these cycles in other systems as well. All right. What you got? So we got through pretty much all the pathway. We talked about the regulation at citric acid cycle, pentose phosphate. We talked about the different layers of regulation at glycolysis, at the citric acid cycle level. We've drawn all the structures really. I know I went through the citric acid cycle kind of fast, but you guys can handle that. You guys can draw that out. We did all that stuff. You got any other questions for me? Can you draw out loose, tight, open? You know how that works? You want me to draw that out?
Yes.
All right, so let's do that. So let's make this exciting. Let's go this and say, let's focus on this. Ooh, so let's draw out our little bell pepper. So here's how we would draw. Let's see. Draw out our bell pepper. So how we can think about this. This looks like crap. All right. Let me draw it out as a different way. We've got like this. This is our open formation. Okay, that's open. Here's our loose. That's hold. Loose. Over here. Over here. So obviously I'm not going to be an art critic on this because you can see how well I draw this. Okay. And then we have our rotor in here. It's going to be contacting usually the wedge, the longer side of the gamma subunit, where it's the widest, is usually associated with the T. So here's our gamma subunit that will rotate in here. And we start out in the 10th state, that has the ATP bound. The loose state has ADP and PI. Loosely held, you could think, it's not forced together yet. And the open is basically empty and available. Okay? So then we could draw this out. So we're gonna go counterclockwise here. Okay, let me draw a different color there. Okay. So counterclockwise, 120 degrees. And then what happens over here? Okay, what was loose up top here now is going to basically be enclosed. Okay, now I'm just going to show it in one frame. So in the book it says, oh, it's tight, ADP-PI, and then it shows another frame. What happens is it squeezes it together in the tight and it forces it to go from ADP and PI to ATP. So I'm going to draw it in less frames, if you will. But the loose had it loosely held, then it rotated, squished them together, made the tight conformation, and they reacted. So in your book it shows you the split second before it was ATP and then after. I'm just showing you this will all happen in a concerted mechanism. This rotates, squeezes these two things together, they react, they're in the tight conformation, they react and they form ATP. Is that okay? So this would be your tight conformation. Now what was tight becomes open, and that ATP left. Okay? And now here, what was open, I guess I drew it as a triangle, we'll have PI and ADP. So here is our open and our loose conformation. So you could draw it like this. Well, that's available now. ADP plus PI can enter if it wants to. Okay. That can leave. And then now our rotor would have turned essentially 120 degrees, and now it's interacting with it in that way. Where it was. And then we can continually go in this cycle. What now is tense? Well, it will have another rotation. It would open up, allow your ATP to leave. It became open. Okay. What was open now becomes loose, so we have our PI and our ADP loose. And what was loose, now we have ATP bound, they've been squeezed together, and again this is another rotation. Gamma. And I'm trying to make it so that wedge, the beefier end, it rotated again. So let me draw an arrow. So it's going to go 120 degrees. That's what I'm trying to show. Not very good drawer at that. I guess that's probably not a word, a drawer. You can see that. ATP left, ADP and PI. And then what happens? What started out now here is in T. You make the full circle. Each one has altered between those different things, so we do another 120 degrees rotation. And we'll say up here, left. Basically, you'll see twice as many in the book because it shows you, oh, it rotated, here's what it's like before, and right after it forms this. But that's effectively, you can see them going between, alternating between those. Is that good enough? Does that make sense? And so, this is what the gamma is doing. It's tied in with the C10 complex. That rotation is powering the machine to physically take these PI and ADP that's here and squeeze them together so that they're now in a confined environment where locally their concentrations with one another is actually very high. And they're compressed together so that they're in an area where they're pressed together. Think about a machine that compresses things and smashes them together. And then when you pull the machine apart, the part that was compressing them pulls it apart. Now what happens? The two parts are smashed together. They've been compressed together. The ATP will quickly diffuse out by diffusion, and before it has a chance to come back in, well, there's such high concentrations of PI out here, it'll jump in. And because this has a gamma phosphate, it can't hop back in and go the other way. So that's kind of how it's all tuned, so that it all goes in one direction. But it's powered by that proton gradient that's physically causing these structural transformations that force the two things together to react. Cool. I like it. Has this been different than any other class you've taken with learned about metabolism? That's good. Don't know if it's a good different or bad different. Different. So I'll take these and I'll try to save a copy of it. Yeah, we got lots of cool stuff up here. And post it. So that's what's going on here, the transition. So you could say powered by H plus 3. Let's see, is there anything else? I think that covers everything. Trying to think of anything else that we covered. Yeah, that's pretty much everything. Can you draw out all those pathways? Can you explain their regulation? What points are regulated? Concepts of reciprocal regulation and different degrees of regulation, substrate level, allosteric regulation, gene expression regulation, and phosphorylation control. All right. Any other questions, concerns? As always, you can keep your criticisms to yourself, unless they're useful. Any useful criticisms? Huh? All right. So it turned out okay. We'll do fine.